All right, this is Erik Wegge, Lab 3. This is the DC motor testing part of the lab. Here is my code, which I copied and pasted from Canvas. The way that it works is that it sets 4 pins on the Raspberry Pi to the values of the 4 pins on the motor controller. Pin 7, physical pin 7 is the pulse width mode on the motor controller. Pins 11 and 12 are the input for motor A, which is the motor that I will be using since the motor controller can do 2 motors. Flipping these between low and high voltage changes the direction in which the motor spins in. Pin 13 is the standby pin. And the way that this works is that first it starts out by spinning the motor clockwise on a high voltage on pin 12 or A and 1, and a low voltage on pin 11 or A and 2. And it sets the motor speed to high using pin 7, physical pin 7. It then waits 5 seconds, so it runs that for 5 seconds, and then it does the opposite. It turns pin 12 onto a low voltage and pin 11 onto a high voltage. And then after another 5 seconds, it resets all of those pins. So here is my circuit. Each of those wires go to a specific place on the Raspberry Pi specified by the code. And the green and yellow wire right here, those connect onto the motor. Oh, I don't know if that's going to focus or not. The motor A part of the motor controller. So if I go ahead and run that code, it starts out, it spins the motor in one direction. And then that little knock right there was the motor actually stopping and spinning in the other direction. And that stops that. And yeah, I believe that's it for the DC motor portion of this lab. Okay, this is Erik Wegge, Lab 3. This is the servo motor portion of the lab. Here's the code, which I copy pasted from the Canvas page. This particular servo motor only has 3 wires. I'll show a picture of the breadboard in just a moment, but it's power ground and then a wire to pin 3 here, which uses the pulse width modulation. This function here is defined in the code as the set angle function, and it utilizes an input to determine how far to turn the servo motor by changing, of course, the voltage over that third pin. I modified the code slightly here because when set angle was run just once with 90 degrees and then the servo motor was used again with the same code, the servo motor wouldn't move. So what I did was I decided to add an extra sleep period to the code, and then I decided to, after 5 seconds, reset the angle to 0. And then, of course, at the end, it stops the pulse width and the pins. So if I go ahead, oh boy, this is going to be interesting here. Go ahead and run the code. Here's my servo motor in my hand. That are the 3 wires going into the Raspberry Pi. The red's power, black ground, yellow is pin 3, and I'm going to try and do this here. I have to be holding the servo motor, so I guess I'm only going to get the comeback. So I don't know if that just got heard or not, but there's the servo motor, and it's going to go back to the 0 position right there. So yeah, that's my code running. All right, this is Erik Wegge for Lab 3. This is the step motor portion of the lab, and here's the code that I copy-pasted from the Canvas page. The first part of the code sets the which pins on the Raspberry Pi are being used for the stepping at 17, well, the BCM 17, 22, 23, and 24. So for that, each of those pins are set to GPIO out, their output pins, and then this sequence here is saved as an array in code, and it's the sequence over which the stepper motor is used. So if this is a 1, that means I think it was pin 17 will be on high, then this is 0, and that's 0, so that means pins 22 and 23 are on low, and then this is 1, so that means pin 24 is on high. And then each of those changes in voltages determines how the stepper motor moves. So the step motor is going to move in clockwise direction right now. This block of code just determines how to set the wait time variable. Step counter is at 0 initially, and then while true, so this code will run infinitely until I tell it to stop. For the range of pins, set the output of that pin to true. Otherwise, set the output to false. So what it does is it just iterates over the range of those pins and changes their voltages from either high to low. And then the step counter is incremented each time that happens. If the step counter reaches the end, what it does is it starts over so that it runs through this sequence here again. So I'll run that code now. Those are the 4 wires that go into the step motor controller. And those are each pin 17, 22, 23, and 24 BCM. There's 5 volts power and ground. And here is the stepper motor controller. Now those 5 wires come out of a plug on the stepper motor, and those lights indicate which of those wires is receiving power in the sequence. The step motor is rotating very slowly. I've been told, though, that this is how it's supposed to work. It's not supposed to be moving very fast compared to, say, the DC motor, and it moves quite slowly. So yeah, that is the step motor for my lab working and its code. Alright, this is Erik Wegge Lab 3. This is my experimental setup for measuring the dynamic torque of this stepper motor. Here, behind all of this duct tape, is a stepper motor with some string duct taped on and then wound onto the shaft of the stepper motor. That string goes all the way down to this Ziploc bag here, which currently is holding about 8 or 9 quarters. This tape measure here is what I used to measure the height of the Ziploc bag right at that point there. Here is my breadboard. Same from the stepper motor exercise. No changes there really. Here is my code. It's slightly different compared to the step motor exercise. Namely, that the code was modified so that when it broke out, it not only would print a time for how long the code has been running, that is actually an example right there, but it would also reset the GPIO pins. So what I'm going to do is I'm going to reset the direction of the step motor so it's 1, and I'm going to run this to show that it works. So there are the lights flashing on the motor controller, and if you look real closely, the Ziploc bag is gaining height. It's moving quite slowly just because of how the code is set up. I chose to keep the rotational speed of the shaft the same as was in the original code, so it's, I think, stepping about every 100th of a second, but it is rotating. So yeah, and then I take the difference between where the top corner of the bag was when it started, and once it's traveled an inch, I'll take that difference in time from the code and then use that to analyze the dynamic torque of the step motor. So yeah, that's about it.